last week. So if we had benzene, we had the compound with 6 carbons connected with double bonds and our hydrogens. And if we looked at our molecular formula, the molecular formula for this would include all of the atoms that went into this structure, which is what? It's our molecular formula for this. How many carbons? 6. How many hydrogens? 6. So our molecular formula takes into consideration what the molecule looks like. So it needs 6 carbons and 6 hydrogens. Our empirical formula is always the lowest reduced, and I can't spell empirical, but it's close enough, is the smallest whole number ratio, which would be, in this case, C1H1. Really where the empirical formula is coming from is experiment. If we go into lab and we know nothing about some compound that we've isolated, we can go through and decompose it into the individual elements, and then we can determine the empirical formula by looking at all of the pieces that came out of that decomposition. Okay? That gives us a little bit of information, not a whole lot, but it gives us some. Okay? The reason why I think it's less and less important now is that we've got a lot of other techniques available to us that can allow us to identify the structure outright. We don't have to decompose it into all the tiny pieces and look at all the tiny pieces to try and put it back together. So empirical formula is something that's kind of disappearing, in my opinion, or will disappear from the general knowledge base because we have better tools than looking at empirical formulas now. That said, it hasn't disappeared yet, so we've got to worry about it. All right, so if we look at our empirical formula, or any formula for that matter, what do the numbers mean? There's 1 carbon for 1 hydrogen. Okay, what if I give you 12, or sorry, not 12, let's do 6 grams of hydrogen. Does that mean there's 6 grams of carbon? Nope. I don't remember what I said. Did I say 6 grams of hydrogen or 6 grams of carbon? Hydrogen. I said hydrogen. If I say 6 grams of hydrogen, does that mean there's 6 grams of carbon? No. Your formula tells you the number of an individual species. It tells you nothing about the mass. Think back to your balanced equation. Okay, your balanced equation doesn't tell you anything about mass. We tried to build a bike, and I told you had 2 bicycle wheels. How many bikes could you potentially make? 1. But if I tell you you have 2 grams of bicycle wheels? Okay, we don't know how many bicycle wheels a gram is, or even 2 grams is. So we can't actually determine anything about how many bikes we can make. So our formulas and our balanced equations tell us the number of that species. It tells us nothing about the mass. Right? And this is where this becomes challenging. If we went into the lab and decomposed, say, benzene into the individual elements, what would we end up measuring? Go into the lab, do you count each of the individual atoms, or do you just get a bulk mass of those atoms? You get a bulk mass. So what we have to do is take that information and convert it into an amount of atoms, the moles or the molecules. Once we're in the moles or molecules, then we can then shuffle it into our formula, because our formula tells us our moles or molecules or atoms. Okay, it's the amount of them, not a mass of them. Okay, kind of tricky. I forgot, I just switched up the order on these slides. So we've got general steps that you can follow for determining your molecular formula and your empirical formulas. Okay, to get to the molecular formula, you have to have the empirical formula first. Okay, so these are all of the steps. For our empirical formula, you'll notice our very first calculation is to do what? Convert everything over into moles. So if we have a mass amount, we get it into moles. Remember when we were doing conversions, what was the first thing you were supposed to do with conversions? Get it into moles. Why? Virtually everything that we use in chemistry deals with moles. The numbers of atoms. It's the number of pieces. When you're building a bicycle, we don't care about the mass of each of the pieces. We care about how many of those pieces we've got. Same thing's happening with chemistry. Okay? How many do we have? So our first step is to get everything into moles. Once it's in moles, we can slide it into a formula. Okay? But then we run into an issue. What if our moles don't come out exactly at a whole number ratio? We get, say, 5 to 1.6. All right, well, our formulas give us what? Whole number ratios or fractions of atoms? Whole number ratios. So our next step when determining your empirical formula is to divide all of those mole amounts by the smallest number. All right, if you go through and divide everything by that number, you should end up getting to pretty darn close a whole number for every single element, because that's how our compounds are built, by whole elements. They aren't built by partial elements. So if we did everything properly, we should get a whole number ratio all the way through. Now that we've got our whole number mole values, we can just plug those into a formula and line up all of our elements and drop in all the whole numbers. Okay? We're looking at just kind of broad terms right now. We'll look at an example in a second. To do the molecular formula, what we'll do is determine the molar mass of the empirical formula. How do we determine the molar mass? Add up what? The mass of each element, which you determine by looking at the periodic table. Okay, so you now have the molar or the molecular weight for the empirical formula. The next step is to divide the actual molar mass, so you'd have to be given that information, by the empirical molar mass. And you'll get a whole number. That whole number is what you need to multiply all of your element values through for your formula. Okay? And again, we'll look at that in a second. So once we've got that, we can then scale it up to what our actual molecular formula will be. So broad strokes, these are our steps. So let's take a look at a couple examples. Or are there questions about that yet? Okay. So we looked at this one. An unknown compound of radium oxide is found to contain 0.726 moles of radium and 12.3 grams, I should say, of oxygen. What is the empirical formula? Well, what should we include in our empirical formula? What do all formulas contain? Every single one of them. Really? It's a chemistry class. They contain atoms or elements. What elements are in this empirical formula for this compound? We have radium and we have oxygen. Do we know how much radium there is? We don't know our formula, so those are technically X and Y. X and Y are supposed to represent the number of moles that would go into this. Okay? Or the number of atoms. Since we're given units of moles, we can stick it in moles. So do we know how many moles of radium are present in this compound?
76.
We know there's 0.726. That sounds a bit odd. Can I have 0.726 of an atom? No, so that's a little bit weird. Right, that's because we haven't gotten to our final step in our calculation. Do we know how much oxygen is present?
12.3 grams.
12.3 grams, but what goes into our formula? Moles. So our very first step is to get all of those conversions, or all of those units for our elements, into moles. How do I convert 12.3, what was it, 12.3? Grams of oxygen into moles of oxygen?
To multiply it by the, or to divide it by the
16, the molar mass.
molecular of
Okay.
the oxygen.
I understand why you're saying multiply and divide. I don't want you to be thinking about it in that way. Because ultimately what that means is you've memorized a formula, and if you mess up the memorization, you could be screwed over.
Well, it's 1 mole over. You
So
have 1 mole per.
moles of oxygen needs to be in the
16,
numerator,
Yeah, 16 grams.
and I need grams of oxygen in the denominator, so my units cancel. All right, what's the conversion between grams and moles?
16 grams.
16 grams is 1 mole. How did you get that number?
On the periodic table.
You go to the periodic table, and the periodic table tells you that that's the molecular weight. Okay? What number do we get out of that? Can we do it? I don't remember what it was. 0.75?
0.75. That's what I wrote down last time. So.
Most reasonable. 0.75 moles of oxygen. So what can we now do with that information? Put it into the formula. Cool, so we now have a formula for this unknown compound. It's R.7260.726. That looks kind of ugly. What can we do to fix that? What was the step from the previous slide? Divide by our smallest number, 0.726. 0.726. What does this give us? R1. That's a good typo there. What element is R? Radium. Need the A in there. So Ra1, and our oxygen becomes 1.09 something. Okay. What is that 1 very, very close to? What is our oxygen very, very close to? 1. What's our formula become? RaO. We've now come up with the empirical formula. Is this potentially, or is this the answer for our compound? Is our compound exactly 1 radium and exactly 1 oxygen? We don't know that. What we've got right now is the empirical formula. It is quite possible that we're looking at a molecular compound that has more pieces in it. Until we actually know more about this compound, we're stuck with that. That's all we've got, the empirical formula. Questions about the work we went through to get that? Yeah?
I have a question about this work, but when you were talking about benzene and it's H6, and you just said, well, it used to just be the smallest ratio. So it's
For the empirical formula,
so you can just go right to C1H1?
yes.
But here, because we have a question, we're able to figure it out. Is it ever going to be more than 1? Like,
In your ratio, it could very well be more than 1. You could have C2H6, okay, which would go down to C1H3.
but if you're just looking at benzene and you already know.
So if you already have the structure, so there's an interesting question. If you know the structure, do you have to do any calculations? No, it's just a question of counting the atoms. Okay, the only reason we go through and deal with the molecular formulas and the empirical formulas is we're trying to find out something about some compound, okay, because we know nothing about it. If we know the structure, there's no sense looking at the formula. It's pretty useless. And that's one of the first lessons you would learn in organic chemistry, because everything we talk about in Gen Chem is here's a formula, work with the formula. Okay? That's just looking at the individual pieces that went into it, but it says nothing about how those pieces were arranged. Lewis structures starts to look at how those were arranged. So if we look back at our Lewis structure and trying to put together those compounds, what did we end up noticing in some cases? There were multiple ways to arrange the elements to match a formula, but give us drastically different physical properties. Right? The structure is the be-all, end-all of what we're trying to do with organic chemistry, or with chemistry in general. We're trying to figure out something about the structure so that we can get to its function. The formula gives us some information. So if we have nothing else, the formula gets us something, okay, but very little else. Right? That would be like taking apart your car and saying, I've got all of these pieces. Now what does this thing do? Right, well, just looking at those pieces, we may not be able to tell that all of those pieces are supposed to go together to make a car that actually moves people. Right? So what we're looking at with our formulas is just all of the pieces and their relative amounts to each other. That gives us some information. That's it. So that's what's happening with our formulas. We're trying to come up with some information. What could we do with that information? Well, we could react it with something else and see how it changes. Right? that's going to give us some more information about that compound, because now we know how it can react and interact with other species. What we're trying to do is take something that we cannot see and throw stuff at it to see how it responds. When it responds a particular way, we can say, ah, I've now learned something about that. It doesn't want stuff thrown at it. Okay? So we've got this giant black box that we can't see inside, and we're just randomly poking at it until we get enough information out to draw a conclusion about what's in it. Everything that we're doing is trying to get just a little bit more information about it. That's what our formulas are giving us, just a little bit of information. And what we did to determine our empirical formula is we took whatever was in the black box, we threw in a stick of dynamite, blew it to a billion different pieces, and then started looking at each of the pieces that came out of it. Said, okay, I can see this, I can identify this, I can identify this. These are all of my pieces. What can I do with that information? Okay, well, we can find out something about what things went into that. Until we take it apart, we can't see those pieces. Kind of make sense? Okay. And this is why I was saying this technology or this process is swiftly kind of going out of fashion. Because why? We have better ways of throwing sticks of dynamite in at our problems. We can now actually open up the box and get a better understanding of what's happening within those structures. Okay, when do you get to learn about those techniques? Well, are any of you taking more chemistry? None of you are taking more chemistry. Guess what? You don't get to learn about those techniques. If you take more chemistry, then you get to learn about those other techniques that are much more fascinating and interesting as far as the application process. But if you don't go further in chemistry, what you have to look at is the very crude systems. Sucks for you. Okay? Questions? It's not that bad for you. Come on, cheer up. Okay, so let's try another system. An unknown sample was found to be composed of 24 grams of carbon and 2 grams of hydrogen. What is the compound's empirical formula? Okay, I'll give you a run at this one. Come up with it as best. We look up carbon. Carbon, it's 12.01 grams per 1 mole. We look up hydrogen, 1.01 grams per 1 mole. We punch that into our calculator. We should get roughly 2. Well, actually, somebody gave me a different number. And we got 1.98 and 1.99. Did I actually put them in the right spots, too? Oh, even better. Okay. When we go through and now try and put this into our formula, okay, we could go through and write this out as C 1.9, I already forgot my numbers, 9, and H 1.98. You may get numbers that aren't exactly whole numbers, but they are darn close. So what should we do? We can go ahead and round up. Okay, when we're talking about darn close, you're looking at maybe an error of 10%. So 0.9 can go up to 1. But if you're at 0.7, 0.6, 0.5, there's probably something wrong with the calculation. Okay, so you'd want to go back through and check your work to verify that. If you run into a situation like that, you should go ahead and talk to me. Because I don't think you will run into an issue like that this semester. Okay, you can see it in the future. So we might say each of those is 2. Right? What's the problem with that? Is that the empirical formula? Why not? Our empirical formula is by definition the whole number or fully reduced whole number ratio. Is C2H2 fully reduced? How do you reduce it?
Divided by this one.
Divide them both by 2, because 2 is our smallest number, and we get C1H1. Okay, there's our empirical formula. Yes, no?
You have to put the ones, or can you just?
Good call. You don't need to put the ones. You could write it as just CH. In fact, that's probably how you would see it on an exam.
So will we be able to round the mass? You know how you get the number off of the periodic table? If you would round it, it would skip a step, wouldn't it?
Yes and no. Typically, I would always do 12 because I'm lazy when it comes to math. You should really be rounding only at the end of your calculation. Okay, so if anybody has to move into 151 or 152, absolutely you have to round at the end of your calculation. For the sake of this class, all of those kind of rounding errors have been mitigated to the point where you don't have to worry about them at all. Okay. Other questions with that? Okay, what's the next step? Talked about two things on that previous slide. I now need to get to a molecular formula. Okay, can I get some more information out of this? Well, with the information provided there, no, I'm stuck. All I can get to is the empirical formula. But if we now take all of that information, which you now all have written down, okay, we have that same compound. That's the exact same question. Let's switch that up. New question. So a small amount of this exact same sample was tested, and we got that same information already. So we've got our empirical formula. But now we know the molecular mass is 78 grams per mole. So the actual molecule weighs 78 grams in 1 mole. What is the molecular formula? All right, what was our empirical formula? C1H1. What is the our molecular mass for a formula of C1H1? A compound of the formula C1H1 weighs 13 grams per mole. How do you know that? You look at the periodic table. 1 carbon weighs 12. 1 hydrogen weighs 1. Is that the mass of our compound? No. Okay, so we have our actual compound with some unknown x's here. Why do we know that they're both x's and not x and y? They're the same. It's 1 to 1 from our empirical formula. So we know whatever that x is the same for both. Okay. That has to equal what? 78 grams per mole. Okay. We did just list off the steps. Okay. Granted, I didn't expect you to fully memorize it or potentially write down all those steps already. But let's give you a little bit, see if you can come up with what x might be. Okay. So was to take your molecular formula, or your molecular mass, 78, and divide it by your empirical formula, or empirical mass, of 13, which equals 6. Okay. That means that our molecular compound is 6 times larger than our empirical formula. How do I get that 6 to translate through my formula? What is 6 times C1H1? C6H6. So what we're doing with our masses is figuring out the ratio. How much higher does it scale? And because our empirical formula is our fully reduced formula, that allows us to go through and directly solve out of this. Right? It just scales 6 times higher. Right? So we can then multiply that 6 through on our empirical formula and we get our final answer. How else could you solve this?
Take the molecular mass and 12x plus 1x equals 28. Figure out that.
Oh, that's a good call. I didn't even consider that one. So from our empirical formula, we know that x has to be the same in both cases, okay, because it's 1 and 1. So what he's suggesting we do is say take the molecular mass of carbon times 12, molecular mass of carbon is 12, times x plus the molecular mass of hydrogen, which is 1, times x, and then set that equal to 78, because that has to come through. Good call. I didn't even think of that one. That works. Okay. Still, to solve that, you still need to know your empirical formula, because it's not always going to be 1 and 1. What if it was 1 and 2? You do it to 2x. Okay? Because it's twice the number of carbons. Okay? One other way to solve it, be surprised if no one tried this method. Was x equal to 1?
No.
How do you know that?
Mass.
The mass is 13. How about x equal to 2? Why not? We check the mass, and that comes up to 26. That's not the answer. How about x equals 3? No? Still didn't add up. How about x equals 4? No? Still didn't add up. Oh, x equals 5. Okay? You can guess and check. That's a really tedious process, and I don't recommend it. But that does work. Okay, so we've got now 3 possible ways that you could go through and solve this. All of them of varying difficulties of trying to decide and time it takes to go through and solve. Okay? Questions about it? Okay.
Oh, I have a question.
Whoops, sorry.
No, it's simple. What
That's
if
good.
you get decimals? We just do the same thing. We round it up to the
Yes,
closest
if you get decimals, round
whole
up to the
number.
closest whole number. Okay? And it should be very, very close with your whole number ratios. Okay? If you're looking at 0.9 up to 0.1, so if we had 0.9 up to 1.1, those would both round to 1. Okay? Anything outside of those ranges, there's something else going on with the question. Okay? Probably a calculation mistake. So there are all our steps again, trying to figure it all out. You will notice that when we went through and did our molecular formula, that we did not use the whole number, smallest whole number ratio. Why? Because that's for the empirical formula. Your molecular formula can have more than that smallest whole number ratio. Okay? Questions? Okay. Into more exciting stuff. Well, I don't know. Maybe it's exciting. Gases. Just like me, a lot of hot gas, hot air. Gases. What's happening with gases? So we've got a couple important properties of our gases. What one says, they can expand and compress uniformly, very low density, and they mix uniformly. All right, we're going to add some more kind of properties to our gases, because what we're going to start to do is define an ideal situation with our gases. Why would we look at an ideal situation? It's a hell of a lot easier to look at an ideal system than it is to look at a real system. So we make up some rules and approximations to say, if I set it up in this proper circumstance, I can start to make conclusions about this experiment or this process. If I look at the real world system, it's going to be off ever so slightly from the ideal situation. But in most cases, when we go through and make those simplifications and approximations, it gets us darn close to the answer. Okay? The next part of this is that gases, as a thing, exert a force on the container that holds them, which may sound a little bit weird. So right now, we have a gas surrounding us. There's air all around us. But I don't feel any force exerted against me. Right? Do you feel a force being exerted against you? You should sure hope you do. Because if we remove the air, if there's no force, what happens to you? All of your particles then go to fill that airspace. There is a force holding you together as a physical object. Okay? Keeping the liquid that is inside you, your blood, your saliva, your spit, your water in your eyes, in that state and not running all over the place in the room. Okay? There is a pressure exerted against us. It may not be as obvious with objects that we're used to seeing as solid. But what happens if we take a balloon and we inflate a balloon by just blowing that air, that very same air that's in this room that is exerting no force, and we fill it into that balloon? What happens to the balloon? It expands. Well, why can it expand? If there's no force, it can't possibly expand. So is there a force? Yes. It's kind of getting at that weird concept again with chemistry. We're looking at things that we can't see, but we can see how they affect our external world. So when we take a gas, it does have this weird extra force. What do we call that force? Pressure. Right? As simply as we could, it's just a pressure. So the pressure of that gas. If we look at ideal gases, so now we're going to do is scale up some of those extra terms. Our gases have a variable shape and volume. But if we look at a particle of gas, we make the assumption that that single atom holds no volume. Which sounds kind of weird. Okay, but we have to make that approximation, because if I now look at a container that holds exactly the same amount of atoms, okay, and I look at hydrogen gas versus chlorine gas, would we expect a different volume for that gas solution if our particles have indeed changed size? Yeah, they're going to occupy more space. But what we noticed that when we tried to fill a balloon with different gases, and we put in the same amount of atoms, we ended up noticing that it gave us the exact same volume. Okay? And this only works up to a certain point. Okay? There's a couple conditions that go with that. One, we have to be at standard temperature and pressure. That's what that STP stands for. Okay, do we have any engineers in here? A couple physicists, maybe? Maybe. Guess what STP means? Standardized, which means standardized means it's the same, right, for everybody? Very unfortunately not true. You talk to an engineer, you talk to a physicist, you talk to a chemist, okay? You talk to somebody working in a lab setting up equipment. STP is different depending on what they are working with. Okay? STP for us, standard temperature, is 0 degrees Celsius. Standard pressure, atmospheric pressure. All right, but how often are we going to work at 0 degrees Celsius? Not very often at all. That's pretty cold. So an engineer looks at it and says, that number is stupid. That's not going to be my standard temperature, because that's not standard. I'm never going to do an experiment at 0 degrees Celsius. So I'm going to make standard temperature 25 degrees Celsius. Understand the logic behind that assumption, but now we're no longer at a standard value. Okay, so watch out for that when looking at calculations, particularly across other fields, is that this term standard temperature and pressure is not as constant as you would like it to be. Okay? So just be aware that that does vary depending on who you're talking to. Okay? So if someone says it's at STP, don't trust them. Say, what is STP? And when they look at you weird, you can say, this is why I asked that question. Okay? So, under standard temperature and pressure, all gases, doesn't matter what type of element we've got, come out at 22.4 liters. That's kind of an odd observation if each of our elements have different masses, which means they have different sizes. So why is that the case? Okay, why does it come out being exactly the same? Okay, well, what we're looking at is the volume that each of those atoms can occupy. Not the atom on its own, but when it's moving, its relative motion towards its size, okay, its relative location where it can move in is much, much larger than the atom itself. Which means, as a first approximation, every particle of gas has the exact same volume. And if we simplify that even further, we're going to say it occupies no volume. So the atom has no volume. But that pressure that the atom can exert on the rest of the environment, that's what's contributing to our volume. Okay? Kind of a weird observation, but we make that assumption. When could that be bad? Well, if we change out of STP, that's a possibility. But what happens if I put in so many molecules that now the molecules start running into each other? I start to vary off of this observation. Okay? So when we're looking at 1 mole of a gas equaling 22.4 liters, that's at relatively dilute, if you will, pressures and moles of our molecules. Okay? If we go up to high enough pressures or high enough molecules within a given space, we start to lose this relationship. Okay? When we shift from ideal to real. What are you guys going to be primarily responsible for? The real situation or the ideal situation? Ideal. Which means if I ask you, or I give you 1 mole of a gas, and I ask you what the volume is, what are you going to tell me? 22.4. What did you do to do that? Get me that number. No? Well, partially, yes. If I give you 1 mole, and I want to know the volume, what are you doing? You're doing a conversion. What did we just give you? A new conversion factor that allows you to relate moles to liters. What is that relationship? 22.4 liters is 1 mole. You have yet a new conversion factor that you need to know and use and manipulate. Okay? So anytime you see these equations with different units on either side, you have a conversion factor. You need to be focusing on how can we incorporate that into dimensional analysis. Okay? Rest of that was all pretty much said on the previous side. We're looking at a relatively low density, expand and compress, mixing uniformly, so we don't get gases sectioning off. Okay? We aren't going to get, if we put in hydrogen and oxygen into the same container, we're not going to get one side being purely hydrogen and one side being purely oxygen. They will mix evenly through the entire process. Okay? Is that a perfect approximation? No, but it gets us pretty darn close.
There's not very any density.
We don't see a density effect when we look at the ideal situation. In a real situation, yes, we have to worry about density effects. Okay? And then the last thing, gases exert this force, and that force is pressure. Okay? So, let's use that to our advantage. How many liters are needed to hold 2.0 grams of hydrogen gas at standard temperature and pressure? Okay, so we'll set this up. What are we trying to get to for an answer? I want liters of hydrogen gas. So we'll use the complete unit. What am I given to start with? I'm given 2.0 grams of hydrogen gas. Any questions straight out of the bat or straight out of the gate with this one? Because if you don't have a question straight out of the gate, I'm going to have a question here. No, not even looking at the conversion factors yet. What's the formula for hydrogen gas? H2. Why is that going to become important?
Because it's going to change the...
It's going to change the molar mass. So when we're looking at hydrogen gas, you have to remember it's one of those diatomic elements. You have to make sure you use H2. Okay? So that's all the help I'm going to give you for the moment. Okay, we've got where we want to get and what we start with. Start to drop in your conversion factors and see what can happen. I'll give you a few minutes to work on this. So we write down what we want and what we have. And we multiply by a conversion factor. Do we have a conversion factor between grams and liters? That is not a valid conversion. We do not have that information. Okay? So that means our conversion is useless as it's written. So we have to change it. What can I convert the grams to? Moles. What have we been saying now for at least most of this lecture? Your first step should be convert it to moles. What is the relationship between the grams of hydrogen and the moles of hydrogen? 1 mole is 2.02 grams. Where'd you get that information? We can get that from our periodic table. Bless you. Okay, what units are we at now? We're at moles because we've canceled out our grams. Okay, is moles of hydrogen what we want for our answer? No. So what needs to happen in our next conversion? I want moles in the denominator, and I want liters in the numerator. Do I have a conversion that relates moles and liters? Yes. What is that conversion? Dude, you guys never have memorized something so fast. 22.4 liters is 1 mole. We now have our conversion set up by following the units to set up our conversion. We can now punch it into our calculator and we can get an answer of 22.4 liters. Okay? It's probably a little bit off from that, but it's close enough. Questions about that? Okay? So when we bring in gases, we have that new conversion, a new relationship between volume and moles. Ooh, you guys want to give this one a shot? I'll tell you right now, this is one of those long ones. Remember how we spent an entire day looking at percent yields and limiting reagents? This is a good practice question. Can't say it's a good thing to waste lecture on right now. All right? So what I will try and go through and do is solve this and record it and post it so you can look at the full solve all the way through as a separate video. Okay? You should be able to solve this one. You have the ability. Okay? I think you can do it. Much more difficult than you'll see on the exam, so we won't stress on that. Questions about it? General pathway, what are we going to have to do? Balance the equation. What else? Turn our grams of aluminum metal into moles of aluminum metal. Then what do we do? Convert our moles of aluminum metal into moles of hydrogen. We won't convert into liters. In fact, we cannot convert into liters. Why not? Our aluminum metal is what phase? Solid. That relationship of 1 mole equals 22.4 liters, that's 1 mole of a gas. We're not a gas yet. So what we'll have to do is convert our moles of aluminum into moles of hydrogen gas. How do we do that conversion? From our balanced equation. Once we have moles of hydrogen gas, what can we do? Now we can convert it to liters. Okay? So you've got 5 steps within that to get through and solve it. Again, you should be able to do it. Good practice. I recommend it. So, back to our gases with pressure. Okay? A bunch of different ways that we could look at pressure. They got a nice little picture here. I was going to do a simple little demonstration. Everybody played with straws in their water or their sodas? You all have done that, right? So you stick the straw on the water, then stick your finger on the top, you pull it out, and you drink your soda real slowly that way, right? Okay. Or you stick it out, put it over someone's head, and go, I'm going to drop it, and then you do, and then they get all wet. Okay. Why is the liquid staying in the straw when you do that?
You're changing the pressure.
Okay. But if I took that straw and stuck it on someone's head and put my finger on it, their head isn't going to magically get stuck in the straw. Why is the liquid staying in the straw? What is holding it in there?
The gas.
What gas?
On the soda or something like that.
Well, if anything, the soda is giving off gas, causing the liquid to come spraying out.
Is the oxygen inside the straw?
Has nothing to do with what's in the straw. It's the pressure outside the straw. The pressure outside the straw is now pushing up on the liquid, keeping the liquid in the straw. It is atmospheric pressure that's holding it on there. Okay? How else could we see that? If you take the straw, Put your finger on the top of it and then stick it in the liquid. Does any liquid make it into the straw? No, why not? Because when you put your finger over the top of it, you now have atmospheric pressure, and you've closed one end. As soon as you put it into the liquid, it still has atmospheric pressure inside it. That atmospheric pressure is now working against the liquid making it into the straw. It's actually pushing the liquid out and keeping it out of the straw. So we have this pressure that's all around us, and it's a question of what we do with this pressure and how we can manipulate it. Okay? So atmospheric pressure is one of our common things that we make reference to. Okay? Why would we make reference to atmospheric pressure? What is atmospheric pressure? It's the pressure around us. Okay? What's interesting about atmospheric pressure? Does that pressure change? It does, pretty drastically, and that has large effects on how we can manipulate other different things, like cooking, right? Or like our ears popping, or our blood staying in our body. Okay? We've got all sorts of issues happening with this atmospheric pressure. There are a variety of ways to monitor this pressure, okay? Because right now we can't really quantify it. We can say, well, it's about that much. You know, just moving my hand through it, that's the pressure of it. If I move to more pressure, I wouldn't be able to move my hand as fast. If I move to less pressure, it goes really fast. Okay? It's kind of a silly comparison. We can't quantify that very well. So what someone went through and observed is if they took a container of mercury, okay, and they took a tube full of mercury, and they filled both of those with mercury, and then inverted the tube upside down. Okay, well, what keeps the liquid in the tube? Atmospheric pressure doing what? Pushing down on the surface of our mercury. If that surface can't rise, then the liquid in the tube can't come out. So what they noticed was that during certain weather patterns or different altitudes, is that the height of that mercury changed because the atmospheric pressure changed. The amount of force, the downward force of our atmosphere on that bottom container of mercury allows the mercury within the tube to either fall or rise. Okay? So if that was our initial quantification of it, what units might we use for pressure? Let's say this was a graduated cylinder. We might use liters, good call, liters of what's in the tube? Mercury. So we could record it as a volume of mercury. Okay? We could also record it, instead of as a volume, we could record it as the distance, the height of the mercury tube. So we end up with in inches of mercury. One of our initial pressure measurements was inches of mercury, or millimeters of mercury, actually. Okay? And it's just about how high that mercury was within a specialized tube. And as long as you use the exact same specialized tube to measure your pressure, you can get consistent readings. Okay? But is that the only unit of measurement for pressure? Anybody know a different one? PSI, pounds per square inch. Just a downward force on anything. Okay? There are other ones. Atmospheres, torrs, kilopascals, pascals. And we have a stupidly large amount of possible, where did it go? Units for our pressure. And what makes this particularly obnoxious as far as you're concerned? Oh, it's not quite that bad. Conversions. You now have to convert each and every single one of those units to any one of the other units. Okay? Just like our English to metric conversions, we now have that with pressures. So the table in your textbook goes through and gives us what each of our standard pressures are and relates them to all of the other units. So if I want to convert atmospheres into inches of mercury, what's my conversion factor? 1 atmosphere is 29.9 inches of mercury. But what if I want to convert atmospheres into kilopascals? 1 atmosphere is exactly 101 kilopascals. All right, so you've got a bunch of possible conversions that can come out of this. When we talked about the Snorlaxi and the Skittlefarts, you're like, oh, that doesn't make that big of a deal. This is, as far as I'm concerned, Snorlaxi and Skittlefarts as far as conversions. Okay? We've got a ridiculous amount of units potentially coming out of these. Why? It's another interesting phenomenon. We can be a little bit nicer than calling everybody idiots. Chemistry is a very old subject. In some cases, we've decided to combine all of our knowledge and say, okay, we all agree that the element that has a molecular weight of 10.81 is boron. And it has the symbol B. Okay? That's pretty consistent from wherever we are. What's happening with pressure? It's changing because a lot of very famous scientists discovered the phenomenon of pressure and built their unit system for it. What happens when you get very famous egotistical people naming something? They never want to change. And so what happens within our units for pressure? Someone got used to using PSI to go through and calculate something, or to do their conversions, or to inflate tires. And they said, I am not changing this, because I already understand these numbers. I don't want to see new numbers. Right? So what does that mean for you? You're SOL, because now you have to follow them. But not only do you have to follow them, but there's another old famous person that says, I'm only using kilopascals, because Pascal was the greatest scientist ever. So now you have to relate PSIs to pascals, and pascals to atmospheres. Okay? I'd go egotistical over idiots, but there's a lot of ego in science. Okay? And that's why we end up associating people's names with a lot of these units and a lot of reactions if you move into organic chemistry. Okay? And it's all just because someone said, I'm not changing this. I want everybody to remember me for the rest of their lives. Okay? And now you can remember them in spite and hate. They can roll over in their graves for all we care. Okay? So you are responsible for dealing with those conversions and getting between them. The other thing that I want to address here is something known as the vapor pressure. If we take a liquid, any liquid, and we just set it on the counter. Well, let's put it in a beaker and set it on the counter. Okay, let's take something like water. Okay, it's a liquid, right? What do liquids do? Fine. Give me the answer right away. Our liquids will eventually turn into gases. But we aren't providing any energy for it to get into a gas. So why is it turning into a gas? Because if I take that beaker and we just leave it in here, eventually all of the water disappears from the beaker. How can it disappear from the beaker if I haven't put it at the boiling point to turn it into a gas? What's happening? Turns out most compounds have what's known as a vapor pressure. Right? We defined 3 phases, solid, liquids, and gases. I would argue that really it's just 2 phases, solids and gases. Then what's the liquid phase? Well, the liquid phase is only a liquid because atmospheric pressure is keeping it from turning into a gas. When we add more energy, what we're trying to do is counteract the atmospheric pressure. But atmospheric pressure is imperfect. Okay? It's not a perfectly closed system. So what happens is a few molecules in your liquid will escape up into that gas phase. Okay? Every so often, the atmospheric pressure pushes it back down and says, get back into being a liquid. So it does. It goes back to being a liquid. Okay? But every so often, if we leave the container open, what happens is that little gas molecule pops up. The liquid comes up into the gas. If it stays in the container, atmospheric pressure is eventually going to push it back down into the liquid. But if the container's open, it can escape the container. Well, if the molecule has escaped the container, can it get pushed back into the liquid? No. So when we look at an open container, sitting on the counter, that liquid can turn into a gas and escape the container, and then we never see it again. But if we look at a closed container, what happens? Does the liquid ever turn into a gas and disappear from your closed container? As long as it's sealed, no, it's now trapped in that state. The atmospheric pressure inside that container keeps it oscillating back and forth between the gas and the liquid. So depending on your compound, you may have a compound that has a very high vapor pressure. What does that mean? It's very volatile. What does that mean? It evaporates fast. Okay? It really has very weak attractive forces between those individual molecules, so it tries to get out of that liquid state as quickly as possible. So if we look at a closed system of something with a very high vapor pressure, when we open it, typically what do we hear? A release of a gas, because there's a high vapor content. The vapor is your pressure, your gas phase. Right? So if we look at a compound with a very low vapor pressure, how long do you think it would take to turn into the gas phase? A really long time. Take a look at liquid mercury. It is a liquid. Very rarely do you ever see liquid mercury disappear into the gas phase. Why not? Its vapor pressure is ridiculously low, to the point that it cannot translate into the gas phase. Water is actually relatively high, which is why when we leave it out, it does translate up into the gas phase, and it can get pulled out of our open container, so it can't get forced back into the liquid. That's what's happening with our vapor pressure. What about dissolving gases in liquids? Okay, well, we can bubble a gas through a liquid. It's going to do the same thing. We're pushing that gas into the liquid state, okay, or into that solution. Okay, to get it in there, what do we have to do? Our gas wants to be free and free-flowing, moving everywhere. Our liquid is trapped. So if I'm going to try and take a gas and put it into the liquid state, what kind of pressure do you think I'm going to have to put behind it? What kind of pressure am I going to have to put behind a gas to get it to go into my liquid? It's going to have to be a very high pressure to force it into the liquid. Because if I can't force it into the liquid, remember, it wants to be free-flowing as a gas. To get it into the liquid state, I have to push it in there and try and keep it trapped in there. Right? So what I'm going to try and do is put as much pressure behind it as possible to keep it in there, and then real quickly close off the container so that it can't escape back out. What's happening with carbonation? What are we doing with carbonation? We take CO2 and we force that into the liquid state, okay, or into our water solution. We aren't changing the phase of that compound. We're forcing it to dissolve in our liquid, okay, be it water or soda, whatever you want to say. Okay, and then we trap it there as best we can by closing the container. What happens as soon as we open the container? Gas, wanting to be free-flowing, starts to come out of the liquid, and we see the effervescence in the bubbles. What happens if we leave that container open? It goes flat. Why? All of the gas that we had trapped in the liquid is now frantically getting out of the solution. Right? The time it takes to go through and do that is going to depend on varying other processes, like solubility, which we'll talk about next week. Okay? So we get some kind of interesting things happening with our gases.
Dry ice just frozen CO2?
Yes, dry ice is just frozen CO2.
I have a question.
Yes.
This is, as we were talking, I was thinking about the vaporizers and the humidifiers for the rooms. So that's pretty much what is happening. You put the water in there, and then the particles of
Humidifiers
break apart.
maximize surface area of the water with the outside air. If you maximize that surface area, you get a higher concentration of water vapor that goes off into the gas state, which you can then collect or fill the room with that moisture.
And do the hydrogen and the oxygen come separate?
No.
When you do that, or it's just
No
water?
element breakage, no bond breakage. It's just water.
Okay.
And we'll talk about bonds versus forces in a little more detail again next week.
Okay.
But we aren't breaking molecules.
Yeah. Okay.
Ideal gas behavior, super important as far as I'm concerned. We already talked about one. There is no volume for our particles. other things with our gases. They move in straight lines, random motion. Okay, so they'll move in a straight line until what? It hits something and causes it to bounce in a new straight line direction. Okay? Gas molecules have no attractive force with each other. Okay? Also not true. But relatively, at a first approximation in an ideal situation, it works. Okay? So we can make that assumption. They collide without losing energy. Okay? We ever seen that be true to the case? You take a ball and drop it against the ground. We say it loses no energy. What should the ball do? Bounce right back up to the exact same height, and it should just keep bouncing. Okay, never losing energy. Okay, so that's also not true. But again, to a first approximation, it's pretty close. Okay, and then the average kinetic energy for your molecules is proportional to temperature. What does that mean? If I increase temperature, what happens to the kinetic energy? What happens to the motion? It increases. It increases. That's all we're saying by that statement. Okay? So this will be just kind of a thought process we will pick up here. What variables might affect gas pressure? Okay. So what we're going to do is pick up there next week. Think about that over the weekend.